Welcome back to the Chem OG. Today we're going to talk some shop about thermodynamics. And when we talk about thermodynamics, there's a lot of stuff going on, but remember that thermodynamics is really all about heat transfers of some sort. So thermo meaning, that we're looking at heat, dynamics meaning that things are changing. And so the first thing we're going to take a look at is enthalpy. Now, enthalpy is symbolized as delta H. So remember that delta means some sort of change in something. And essentially what we're measuring with enthalpy is the energy change that's caused by a reaction. And so there's a couple of scenarios that can happen. Either we can get an energy release. And when you have an energy release, right, when you release some energy, that means you have less energy than you did before. And so any process in which there's an energy release is going to be associated with lower energy than what we previously had. And remember that when we have a lower energy, it leads to stability. So when we have an energy decrease or an energy release, that's known as an exothermic reaction. And exothermic reactions are generally associated with products that are more stable. We're creating something of lower energy than that with which we started. And so that means that we're looking at something that is more stable relative to what it was previously. The opposite is an endothermic process, and that it involves an energy absorption. So EX, that makes me think of exit. And so that's what's happening to energy, that it's getting released, it's exiting. Whereas an energy absorption, on the other hand, it means energy is coming into the reaction, and into kind of sounds like endo. And so endothermic energy coming in, exothermic energy leaving. So that's one aspect that we'll talk about in terms of what happens when a reaction proceeds. Another thing we can talk about is the entropy change. And you want to think of entropy change as the change in molecular freedom of a system. Now that may be a little bit of a different definition from what you're used to. So generally speaking, when students learn about entropy, they learn about words like disorder and chaos and randomness. And so all of those are kind of words with negative connotation. And so you want to take a look at what's actually happening on the molecular level when entropy changes to occur. And so what we're really concerned with is, are the molecules more free than before, or are they less free than before? Whenever we have a delta S that is negative, what that indicates is that molecular freedom is restricted. And it kind of is what it sounds like. When you have a restriction of freedom, that means that your molecules can't freely move away from each other, and that generally is a bad thing. You don't want your molecules restricted in terms of their movement. There's a lot of bad interactions that can happen. Usually what's favorable instead is when we enhance molecular freedom, when we have a delta S that's positive on the other hand. So again, don't think of entropy changes as being disorder, chaos, or anything like that. What you want to think about it, or the way you want to think about it, is that it's molecular freedom. If we make more freedom happen, then that's a good thing. That helps the reaction proceed. When we have a restriction of freedom, that makes our reaction not willing to occur. Okay, so there's the energy aspect of a reaction. There's the entropy aspect of a reaction as well. If we want a favorable reaction, it has to have at least one of the following characteristics. If it has both, awesome, but it has to have at least one of the following characteristics. One is that we would like an energy release, right? So that way our products can be lower energy, they can be more stable. So favorable reactions are helped by having a negative delta H. Favorable reactions are also helped by having an increase in freedom, right? If we can get our freedom to increase, that also helps for setting up a favorable reaction. And when I say a favorable reaction, I mean a reaction that kind of happens on its own without needing any extra help. Like they're tenets in place that help a reaction move forward. And so an energy release and an entropy increase would be amazing. In fact, if we have both of those things at the same time, then the reaction is guaranteed to be favorable, or spontaneous is another word that we use. It's guaranteed to be spontaneous without any outside help necessary. And the opposite is true too. If you give me a reaction that involves an energy increase, which is bad, and an entropy decrease, which means freedom is restricted, if you're telling me that I'm supposed to have a higher energy at the end, in other words, my molecules are less stable, and you're telling me that there's a restriction of freedom and both are happening, then that's going to lead to an unfavorable reaction. So if you want a favorable reaction, you want delta H to be negative and delta S to be positive. If you want an unfavorable reaction, you want delta H to be positive instead and delta S to be negative. And so what we're looking at in terms of knowing which way our reaction is going to happen for sure is that the signs of delta H and delta S are actually going to be different from each other. So again, just to reiterate, an unfavorable reaction has at least one of the following. It's going to have an energy absorption or an entropy decrease. And if it has both of them, then the reaction is guaranteed to be unfavorable. So notice in those two situations, like I said, the signs of delta H and delta S were opposites of one another. But what happens if delta H and delta S have the same sign? In other words, we're going up in energy, which is bad, and we're also going up in terms of freedom, which is good. So it's like, all right, which one do I lean on here? And this discussion so far has been a little bit abstract. Let's take a look at a concrete example. Let's say that we're looking at an ice cube that is melting. And so what it's doing is it's transforming from H2O solid to H2O liquid. So let's take a look at the two different variables that we talked about in terms of energy and in terms of entropy, and taking a look at what's happening there, both enthalpy and entropy. So if we take a look at the enthalpy side, what we have to do in order to go from solid to liquid is we have to break intermolecular bonds. Okay, so we're not breaking any of the bonds inside the molecule. It's still H2O on both sides, but what we are doing is that we're breaking intermolecular bonds. And anytime you break bonds, that requires energy every single time. So that means that our energy is going up. That's a bad thing. The other thing that happens in terms of entropy is that when you go from solid to liquid, you're making your molecules more free to move, right? And a solid, things are tightly packed. There's very little wiggle room. Well, when you're taking a look at a liquid is definitely a lot more fluid. The molecules are a little bit more free to move around, and they can actually, be able to adjust their volume to whatever, to sort of kind of spread out depending on what space their container allows. And so when I go from solid to liquid, I have enhanced molecular freedom. And these two things are kind of at odds with each other. And so if I ask you, hey, I got some water, is it going to be the solid form or is it going to be the liquid form? Which side of this reaction is going to be favored? The delta H is pretty decently set. The delta S is pretty decently set, but we know that there are conditions that favor having solid ice, and we also know that there are conditions that favor forming liquid water. And so our tiebreaker here, right, whether we form ice or whether we form liquid water is going to depend on exactly what you think it's going to depend on. It's going to depend on temperature. Are we at a temperature that is in a freezer, for example, in which we can form those ice cubes? Or are we at a temperature where it's like room temperature and you don't expect ice cubes to form on their own, you expect water to remain as a liquid? So temperature is going to be our tiebreaker here in scenarios like that melting ice cube in which delta H and delta S are the same sign. And so it's not really clear which way the reaction is going to go. Temperature is going to dictate which side is going to be favored. So the favorability of a reaction, it depends on enthalpy, it depends on entropy, and it depends on temperature. And so the way that it depends on all of those things is our Gibbs Free Energy Change equation. So delta G equals delta H minus T delta S. And delta G is known as the Gibbs Free Energy Change. And what it does is it encapsulates all those different variables that we talked about previously. What's the enthalpy like? Are we absorbing energy or are we releasing energy? What kind of freedom are we looking at? Enhanced molecular freedom or restricted molecular freedom? And it also captures this temperature term as well. So anytime you use this equation, make sure that you're using a temperature of Kelvin. So anytime you have a temperature in an equation, as a good rule of thumb, it's always a good idea to use the Kelvin scale and do not use the Celsius or the Fahrenheit scale. And so when we have a delta G that is positive, well, look at the things that contribute to a positive delta H. It would be a positive delta H. Look at things that contribute to a positive delta G, excuse me. It would be a positive delta H. And a positive delta H means energy is going up. That's not good. And it would also be a delta S that's negative. So that way the negative cancels out with the negative and we get a positive value for this overall quantity. And so if I have a negative freedom, right, less freedom, and I have higher energy, that's going to lead to an unfavorable reaction. And the opposite is true too. If I have a negative delta H and a positive delta S, that's going to lead to a favorable reaction. And when we have a favorable reaction, we call that an exergonic reaction. When we have an unfavorable reaction, we call that an endergonic reaction instead. So the Gibbs free energy change of a reaction depends on the enthalpy change, it depends on the entropy change, and in cases in which those two signs may be opposite one another, it's really going to depend on temperature to help us break that tie. Thank you so much for watching today's video. Please be sure to hit the like button. And if you haven't done so yet, please make sure to subscribe to support this channel. See you at the next video.